Mixtures of gases. A lot of gas samples are not actually pure, just one single gas, but they're mixtures. Air is a mixture of many gases. This gives us the composition of dry air. 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and the rest of it is made up by a bunch of other gases. So air is a mixture. Dry air means zero humidity. Yeah. Because if it's humid air, then there's water in the gas state in the air, which is normal. And then that would be part of the percentage as well. So in some applications, we can actually treat a gas mixture as a single gas. Because when we measure pressure, volume, and temperature, it pertains to the moles of gas, but it doesn't really matter what those moles of gas are. We can treat it as a single gas. So we can calculate the total moles of molecules in an air sample, even if we don't know which molecules they are. And so we can do calculations and predict things and do all kinds of stuff without really caring exactly what the gas is. And that's because gases behave independently. So Dalton's law of partial pressures helps us to understand gas mixtures. So when you have a mixture of gases, each gas is going to exert its own pressure. The pressure of a single gas in a mixture is called the partial pressure. So it's a little bit like if you think about three people in an elevator. And if you spend any time in elevators, you end up reading the little sign at the top, right? And it says the maximum weight that elevator is rated for. Well, how do you figure out the weight of three people in the elevator? You add them up, right? Because each person has their own weight, their own gravitational force, attraction that they are exerting on the elevator. Well, in a mixture of gases, each gas exerts its own pressure because each gas behaves as if it was the only gas there. And we're going to talk about kinetic molecular theory and about why it is. But for right now, we're just saying this is what happens. So we can calculate the pressure of a single gas in a mixture. The pressure of the single gas is going to be the number of moles of that gas times RT over V. And what Dalton's law of partial pressure says is that to find the total pressure, you just add up the pressures from each individual gas. Just like in the elevator, to find the mass of all the people in the elevator, you just add up their individual masses. That's all this is. So the total pressure is the pressure from each individual gas here, A, B, C, however many, and you just keep going. Now we just looked and saw that we could calculate the partial pressure of that gas if we know the number of moles of gas A. It would be gas A times RT over V. The pressure of gas B would be its moles times RT over V, etc. And if we factor out the RT over V part, then we see that the total number of moles of gas times RT over V is equal to the total pressure. So that's kind of a circular derivation thing there. We can also see that the ratio of partial pressure of a single gas to the total pressure is equal to the mole fraction of that gas. So here, the partial pressure of the gas is its number of moles times RT over V. The total pressure of the whole mixture is the total number of moles times RT over V. And so if we look at the ratio of the pressure of one gas to the total pressure, we've got the ratio of these two quantities. The RT over V cancels out, and we find that we have the number of moles of the one gas over the number of total moles. And that's called the mole fraction. It's not a percentage, but it's a fraction. If we multiplied it by 100, it would be a percentage. So we give that the symbol capital X. So the mole fraction of A is the number of moles of A divided by the total number of moles. And we can use this relationship, ignoring this part in the middle, to find the partial pressure of the gas or to find the number of moles. So this is a useful equation down here. Let's go right here. And that can be rearranged into this, which is perhaps even more useful. The partial pressure of an individual gas in a mixture is equal to its mole fraction times the total pressure. So the mole fraction is equivalent to a percentage divided by 100. A lot of times they'll give you a percent, like they did in that table telling us the composition of air. Nitrogen has a 78% composition of air. Air is 78% nitrogen. So then the mole fraction of nitrogen is 0.78. So to find the pressure exerted by nitrogen, we take its mole fraction, we just convert that to a decimal, and multiply it by the total pressure. So at atmospheric pressure, the partial pressure of nitrogen in air is 0.78 atmospheres. And I don't really have a good answer for why would you want to find that out. There's so many things that you're not really interested in, but we make you learn how to calculate them, right? Look at all the words in this problem. Yeah. Okay. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. Very nice. Do we need to know that? Not really. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. So this might be a situation where you might want to draw a picture. So here we have a piston assembly, and so here's our container. And inside of this, we have 5.5 grams of helium. We have 15.0 grams of neon and 35 grams of krypton. They're inside of that. And the conditions inside there are STP. STP tells us that the pressure is 1 atmosphere and the temperature is 273 Kelvin. They want us to find the partial pressure for each of these three gases. Dalton's law of partial pressures tells us that the pressure of the helium plus the pressure of the neon plus the pressure of the krypton is going to add up to the total pressure. What is the total pressure? 1 atmosphere. I already have 1 atmosphere. I wanted to write PT. That's the total pressure. Now, we had that equation. Partial pressure is equal to mole fraction times total pressure. So we know the total pressure. Could we figure out the mole fraction for each of these gases? Yes. They gave us masses. Can we do it with masses? No. Because gases behave in relation to the number of particles, not in terms of mass. So we need to convert all of these to moles. So for helium, 5.50 grams, we're going to divide by the molar mass to get the number of moles. So 4.002. So 1.3743 moles of helium and 15 grams of neon divided by 20.18. I'm going to write 20.18. I don't want to do that. 74331 moles of neon. These molar mass type calculations should be old hat by now. That's why I'm not writing it all out. And krypton is 83.8. So we'll take the number of grams of krypton, 35, divided by 83.8. And we get this many moles, 0.41766 moles of krypton. How do we calculate the mole fraction? The moles of the individual gas divided by the total moles. So we need the total moles, so we're going to add all these guys up. 1.3743 plus 0.74331 plus 0.41766. 2.53527 moles. That's the total number of moles. Where does the uncertainty lie? It's the second decimal place. Because this top number has uncertainty in the second decimal place. And these have uncertainty in the third. And so then this final result here will have uncertainty in the second decimal place. And so we do retain our three significant figures. So then, there's just not enough space on this. So I'm going to do what I sometimes do to cheat and make more space. What? It's a white marker. Yeah, just goes over everything. And now I've got more space. Okay, cool. Hey, I can. Why shouldn't I? It's not a good model for life. Okay, so we need a mole fraction. We need the mole fraction for helium. So the mole fraction for helium is the number of moles of helium divided by the total number of moles. So I'm going to put that total number of moles in my memory of my calculator, so I don't have to keep doing this. 1.3743 divided by, so I get a mole fraction for helium of 0.54207. Anybody else get that? Okay, good. So then the pressure, the partial pressure for helium, it's the mole fraction times what? The total pressure, right? The total pressure is 1 atmosphere. So for helium, it's 0.542 atmospheres. Because remember, we're doing this guy down here. The partial pressure for the gas is equal to its mole fraction times the total pressure. In this instance, the total pressure was 1 atmosphere. So that works out kind of nice because then the mole fraction is the same as the pressure. So then we need the mole fraction of neon, which is 0.743 0.4331 divided by that old number there. .293. That's the mole fraction, which has no unit. And then we're multiplying that by 1 atmosphere, the total pressure. And so that's 0.293 atmospheres. So that's another one. Let's do this guy. What's the easiest way to get the third one? Subtract. These guys, all three of them have to add up to 1. So if I take 1 and subtract the pressures of the first two, I'll get the pressure of the third one. 0.165. So the partial pressure for the krypton is 0.165 atmospheres. And yes, it's a big old mess. But things are mostly labeled. And there's boxes around the answers. Any questions? So this is a new relationship we're giving you, this guy right here. I'm not going to elaborate on this very much. Your book goes into more details. If you're at all interested in scuba diving, deep sea diving, these concepts of gas mixtures and pressures and things have a very direct bearing on scuba diving. So here's a range of oxygen levels. Okay, and so oxygen's a good thing, right? We need oxygen to live. But oxygen can be toxic at too high of a pressure. Anything can be toxic. And I think that's something I wish I could get everybody in the world to understand, is even water is toxic at certain levels. I'm sure you've all heard stories of people who, died in contests or whatever because they drank too much water. And you dilute your electrolytes and you don't have enough potassium left in your body and your heart stops. And you die from drinking water. So, on one hand, you could be really paranoid and say, oh, nothing's safe. Well, I guess that's true, that maybe you should just, crawl into a corner and die and get it over with. But it's really more of a kind of a moderation thing, okay? So, yeah, there's lead out there, and there's mercury, and there's pollutants in the air. But at certain levels, they're fine. There's fluoride in your water. Yeah. But here's this scale, and between 0.21 and about 1.4, well, I guess you're 1.6. No, 1.4. Here's the range of safe pressures of oxygen. Well, here's your mixture of air, and at the surface you've got 0.21 atmospheres, which is very nice. That's what you're used to. When you dive down, though, the pressure increases. And because the total pressure is increasing, the partial pressure of oxygen is also increasing. And now your level of oxygen is coming up to 0.84. Now, this is still within the safe range. But if you keep going down, you're going to get into a range where it's not safe. And your compressed air, while it is keeping you alive, could also kill you. And so that's why divers sometimes use different mixtures. Heliox is one. It's got helium and oxygen in it. Makes you all squeaky voiced, but nobody can hear you talking underwater anyway, so that doesn't matter. But there's a lot of implications for scuba diving with these gas laws. And I would encourage you to read that in your textbook. I'm not going to test you on it, though. Collecting gases. The easiest way to collect a gas that's being generated from a reaction is by having that gas displace water from a container. And because the gas is now in the presence of water, we're also going to have water vapor in that collected gas. It's going to be a wet gas, not a dry gas. And wet gas doesn't mean that it's raining inside the gas or anything. It just means that there's water vapor inside the gas. The partial pressure of the water in the gas state, we call it water vapor, is the vapor pressure of the water. And this partial pressure of water depends only on the temperature of the water in the gas. And so we can actually look this up in a table. Other people have done all these lovely measurements for us, and we can just look it up in a table. And here is an example of a table. Some of them are more detailed. This one's going by 5 degrees Celsius increments. And so we see at the freezing point of water, the partial pressure of water in the air above that ice is going to be 4.58 millimeters of mercury. That's very low. As the temperature increases, it makes sense that the pressure of the water vapor increases, because which evaporates faster, warm water or cold water? Warm water, right? So as we go up in temperature, the vapor pressure of the water increases, and when we get to the boiling point, at the boiling point of a liquid, its vapor pressure is equal to the atmospheric pressure. So we get up to a maximum of 760. So this is an example of collecting a gas over water. That's the phrase we use, collecting a gas over water. So here we have a reaction, and we're reacting zinc and hydrochloric acid, and this is generating hydrogen gas. And the hydrogen gas builds up a pressure, and it's trying to get out, because that's what gases want to do. And so we have a tube here for it, and it goes through the tube, and it comes under this inverted container, which was originally full of water. And the gas bubbles up, and as the gas comes in here, it displaces the water. And so what we have now trapped above the water is the gas that we're interested in, but we also have water vapor, because here's the surface of water and the water evaporates. The nice thing is, if we know this temperature, we can just look up in a table and find the water vapor pressure. And then we can just subtract it from the total pressure, and the rest of the pressure there is from the gas that we're interested in. So here's an example. A sample of acetylene is collected over water. Anytime you see this over water, tell yourself, I'm going to need to use Dalton's law of partial pressures and subtract out the pressure of the water. The total gas pressure is 738 torr. The volume is 523 milliliters. At the temperature of the gas, which is 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? Now, you do not have to memorize the water vapor table. Okay? You don't need to do that. I'll give it to you, or like this, the value you need will be in the question itself. We just go look those up. We don't memorize those. Okay, so we got a couple things going on here. So let's draw a picture, because pictures can be helpful. So here we've got our container. We collected this acetylene, we collected over water. So here we've got the acetylene, the C2H2. And what else is in that space? Water vapor, H2O gas. And what are they telling us about this gas sample? They're giving us a total pressure of 738 torr, and they're telling us the volume, 523 milliliters, and they're telling us the temperature, and they're always going to give it to you in Celsius, and you always have to convert it to Kelvin. 273 plus 23 is 296. And then they're saying the vapor pressure of water, so that's pH2O, is 21 torr. What are they asking us to find? Yeah, the grams of acetylene, C2H2. So what can we calculate with PVT of a gas? We can calculate moles, right? So we need to find the moles of the acetylene, and then they gave us the formula so we can calculate the molar mass and convert it to grams for the final answer. If we want the moles of acetylene, we use the total pressure? No, because that'll give us moles of acetylene plus moles of water. We need to use the pressure of the acetylene by itself. That total pressure is equal to the pressure of the acetylene plus the pressure of the water. There's two gases in there. It's a mixture. They each exert a separate pressure. Those pressures add up to the total. So what's the pressure of the acetylene? We're going to take 738, the total pressure, and subtract the 21, right? Don't think too hard about the math here. So the pressure of the acetylene then is the 738 minus 21, which is 717. The most common mistake in a problem like this is that a student will forget to do this, and they'll calculate it with the total pressure, and then your answer's wrong. So we're going to rearrange PivNert, and N will equal what? PV over RT, right? If you have any issues rearranging equations like that, please come and talk to me. But I'm just going to assume that we're okay with that. Okay. Are the units on our pressure, volume, and temperature appropriate for using PivNert? No. We need to convert torr into atmospheres, and we do that by dividing by 760. See, I have room, so I'll show that. 1 atmosphere, 760 torr. .94342 ATM. How our temperature is okay, right? What should our volume be in? Liters. So that's going to be 0.523 liters. And now we're good. 0.9494. That's a 0. Oh, I'm just going to start that over. 0. I sure wish my life had a go back button like that. Wouldn't that be nice? 94342 atmospheres. That's the pressure, and the volume was 0.523 liters. And then we're dividing by 0.08206 liter atmospheres per mole Kelvin. I know you guys are tired. If it makes you feel any better, I have a headache. And the temperature is 296 Kelvin. divide by 0.808206, divide by 296. I came up with 0.0203. Did I do that right? Thank you. So N equals 0.0203 moles. We have to convert that to grams. We need the molar mass of C2H2, so that's 12.01 times 2 plus 1.008 times 2, which is 26.036 grams over 1 mole. Coming up with 0.529. Zero 0.529 grams. Any questions?
The 523 milliliters is not their water vapor in there,
Yes, there is.
but we're counting that.
The volume includes water vapor, but those gases act independently. So that's the volume
Okay.
of
So
the
we take
water
the partial
and-
pressure of the gas divided
yeah.
by the total volume, it'll give us the partial pressures.
So we just have to be concerned about the number of moles and the pressure in terms of which is part of the mixture or not. Because they're all going to have the same volume. And we'll understand that a little bit more when we talk about the theory behind it. Any other questions?